uh, machine learning and reinforcement learning. Okay, Hayan, can you hear me?
Yes, I can.
Would you shortly introduce the movie and show us that movie?
Okay. Morning, everyone. As Professor mentioned in the last lecture, I've prepared a short video clip on YouTube about a movie called Back to the Future, which was actually released in 1989. Basically, this clip shows the technologies that Back to the Future got right for 2015. In the movie, the characters time travel to October 21st of 2015. Interestingly, at the time it was filmed, which was in the 80s, 2015 was considered very far future, whereas now we are living in 2021. So I hope you enjoy this clip and be aware that this YouTube clip itself was made in 2015, so it may be a little bit old. I hope you enjoy.
California.
When are we?
We're descending toward Hill Valley, California at 4:29 p.m. on Wednesday, October 21st, 2015.
2015? You mean we're in the future?
This is heavy. The cult classic Back to the Future Part 2, which was released in 1989, has now caught up with times, and the real October 21st, 2015 isn't far off from the one that the filmmakers imagined. Sure, we may not have clothing that self-fits, or dress like this.
All kids in the future wear their pants inside out. Put on this cap. Perfect. You're the spitting image of your future son.
But other predictions hit closer to the mark, or at least are giving companies mentioned in the movie a chance to cash in on the anniversary.
Our laces, all right.
And lo and behold, Nike is rumored to be releasing self-lacing shoes this year in honor of the anniversary.
Does this power lace?
Not till 2015.
All I want is a Pepsi.
In the movie, there's a product called Pepsi Perfect, and right on schedule, the company is releasing a limited edition run of it. Pepsi Perfect, the future is now. Though it's just normal Pepsi in a replica bottle. And if the Cubs manage a comeback and defeat the Mets in the National League Championship Series, they'll have a shot at winning the World Series.
Wait a minute. Cubs win World Series.
Here are some more futuristic predictions the filmmakers got right, or close to it. Video calls.
Hey, the Big M!
Taking Skype calls or FaceTiming is part of everyday life for Americans in 2015. Paying for services with your fingerprint.
Here.
Apple Pay and Samsung Pay have made this a reality. How about hoverboards?
He's on a hoverboard!
Two companies, including Lexus, have been working on prototypes for hoverboards. And then lastly, there are flying cars.
Like DeLorean?
Well, sort of. A Slovakia-based company has a flying car in the works. Now, if only Jaws 19 could be a reality.
Thank you. Can I can I change the window, Hayan? Oh, so Hayan, is that end of the clip? Okay, now I will start.
Sorry.
Hen, I found that the movie was released, the Back to the Future movie was released in 1989. And that was my first year as a graduate student at the University of Michigan. So that's why I vividly remember the movie. And I also found that Michael J. Fox took the time machine to reach to 2020, am I right?
2015.
2015, okay. So I think the Michael J. Fox was the most favorite movie star at that time to me and to my family. Michael J. Fox has another TV show called Family Ties. there was a sister of Michael J. Fox in the movie, and she was so nice person. And I have a daughter. Her English name came from her.
Oh,
That's how much I like the Michael J. Fox and her shows. Um, I imagine that Michael J. Fox can go back to the future and back to the past because of the time machine. So that is the kind of imagination, but unless we find the time machine which can fly as fast as the time of the flight of the light wave, that is very fast, uh, but human cannot do that. But in the digital world, in machine learning, we can go back to the future and back to the past. And that is called forward propagation and backward propagation. That's why I'm going to give you a lecture on time machine today. But because we are all engineers, I cannot show or I cannot make a movie like J. Fox. So I will show more mathematical formalism. Please forgive me for that because I have only that kind of capability, only mathematics, not enough I'm not good enough to make a movie. For the simplicity of analysis, I will consider only a case of 3-layer. Generalization of these 200 of layers and millions of nodes are very straightforward. So to make it very straightforward, I will drive equation only for the case of this very simple case. X is input layer, H is hidden layer, Y is output layer, and there is a connectivity W1 and W2. W1 is the weight matrix to make a connection between input vector X to hidden layer output vector. And the W is the connecting from hidden layer output to a total output layer. When we have an input, we have to calculate output that is called forward propagation. There will be many matrix calculations and activation function, and then we compare the target value and output value that is called cost function. With the given cost function, we update W1 and W2. That is called backward propagation. This is the case of supervised learning, saying that if the our calculation result y is not very close to y dash, that is the real number. This is the case of supervised learning. Then we update W1 and W2. And when we are updating the W1 and W2, we use gradient distance equation saying if this is cost function, we calculate the derivative and we partially update, and finally we wanna go to a point where output of this deep neural network is equal to the real number. That is, I would say, the condition of optimal weight. I think this forward propagation and backward propagation will be conducted. I think this iteration loop will be conducted billions and billions times. If we have more and more data, we can do more of these iterations. Then this deep neural network will be smarter and smarter. Now, At this moment, key equation to update this W1 to make it optimal value is called this equation. This equation is called gradient descent equation. And this is the symbol of backward propagations. Now, in this simple case of 3 nodes, I would like to derive this equation. Let's start. In order to do that, I will start to derive equation for to make an update equation. I should be able to derive this equation. So at this moment of the class, I'm going to spend some time to derive this equation. So that's why we need mathematics in deep neural network. I will start with W2. So now we will start with the derivative of cost function with respect to W2. W2 is the weight matrix connecting H to Y. And then cost function is the square function. So square function derivative came to this value, this equation. This is very basic mathematics, which we learned from high school. Then also we have to make a derivative of this y. This actually coming to here. This y dash is constant, so we don't need to worry about the derivative. In this case, we assume that y is sigmoid function. That means the activation function, we assume if there are many different type of activation function, but at this moment, I will assume that for the simplicity of analysis, I will assume that this y output of hidden layer is conditioned by sigmoid activation function. Then you remember that in the previous class, sigmoid function is actually a form of itself and 1 minus g. I think that was what we derived in the previous class. Then we can substitute the second part of this derivative using this equation. Then our mathematics formalism will become very easy. At this moment of class, you enjoy what I'm doing, but later if you wanna make yourself more confident on this theory, you can spend a little bit of time to derive this equation. Then now this came from the mean square error derivative. This came from the sigmoid derivative, and this is actually the parameters inside the sigmoid function. That's why h will come out from the derivation. So finally, we found that Now, we are in the progress of backward propagation. So please look at that this updated equation. We know y and y dash. Actually, y is the output of this deep neural network. Y dash is the target value to be trained to. I mean, that is the labeled output. So our purpose is to make y and y dash as close as possible. That is the definition of cost function. So if we know this differentiation between our target number and our output, this alpha is the learning rate, usually 0.001. And then if we know the output y and 1 minus y and output of hidden value, then we can update W2. So let's assume that we have a deep neural network. We have an input vector and we have output vector. And if we have the target value, and let's assume that we have some hidden vectors inside. Once if we define cost function, and activation function, with given this value, output and the target value and cost function derivative and activation derivative and some hidden values, we can update W1 and W2. That is the very essential part of backpropagation. Later in this class, I'm going to talk about typical deep neural networks such as convolutional neural network and recurrent neural network and LSTM. All the principles are same. In the case, there are supervised learning, unsupervised learning, and reinforcement learning. But for the case of supervised learning, the basic principle is like that. With given output and the target value and some derivatives, we can update this weights. So we can repeat this process again up to a point that y and y dash is less than certain value. We can stop backpropagation for the propagation. Surprisingly, AlphaGo and AlphaGo Zero, they are using the convolutional neural network to to train them to be able to play the game of Go. But basically, they are doing the exactly same backpropagation. I think in this whole class of this semester, most important part of my class today is that the most important part is I think that this backpropagation. But mathematically it is same. But surprisingly, by combining forward propagation and backpropagation, this deep neural network becomes really, really smart. But I want to emphasize that there are huge number of forward propagation and backpropagation. This is a kind of time machine. Who in real physical world, if we want to take a time machine, we should be able to fly as fast as the speed of light, 3 times 10 to 8 meters per second. But in the deep neural network and machine learning world, who is doing backpropagation and forward propagation? I think computer is actually doing those work. Here, in digital world, time machine is what?
Computers and computing power.
Computer. In time machine, they may have some engine to make them fly as fast as the speed of light. Who is the engine of computer? GPU and DRAM. And GPU and DRAM has to be closed as fast as possible. Later on in this class, we are going to talk about that. Most advanced GPU and DRAM architecture at this moment is HBM. That is the research subject of our lab. That's why we are spending so much time in our laboratory. Students are doing PhD and master degree to design the HBM, because HBM is the engine of time machine in digital world. Junsang, can you understand that? Can you enjoy?
Yes, Professor.
Yeah. But in right now, I'm driving equations for only 3 layers, but in deep neural network, this number of layer could be 100 or in the future 1,000. So it will take more and more equations. But basically, this one-step backpropagation equation is the basic stone to build up all these backpropagation equations. But it doesn't matter whether the number of layers is 100 or 1,000. Same principles are applied to derive this updated equation. Another important part of this machine learning is that in order to make this neural network more smarter and smarter, we need to do the more iteration. More iteration in a short time, we need strong computer. Second requirement for this supervised learning is that in order to do the iteration, we need some data and some labeled data. So to make during the AlphaGo, they gathered all the record of the Go games from the internet. So we should be able to have some structure. So we sometimes call it is a platform. Google has very good platform. Amazon has good platform. So they can have some business opportunities to gather input data and label the output data. So if we have millions or billions of those data, we will have more iterations. That means that we can have more smarter deep neural network and deep neural network. Also, we found that if the number of layer is higher and higher, we found that it is becoming more smarter and smarter. So Michael J. Fox made he was the actor of the Back to the Future movie. Now we are playing a game or making a movie in digital world deep neural network. Your students can be a Michael J. Fox in the computer world. You can write a coding. For example, Junsang, Haeun, and Sangguk, and many students in our lab are making some coding program to do the to combine the reinforcement learning and machine learning. So you are movie star in this computer world. If I speak Korean language, I can really make it funny, but this is my limitation. Now, you know what? What I did so far was to derive equations for updated equation for W2. Now, I would like to spend some time to derive equation for W1. And by making some connection between W and W2, we can complete the updated equation of gradient descent. If we are successful into making a connection between W and W2, of course, W1 to W100, those relationships can be derived as well. Then we can just writing a code and computer will do all the backward propagation. As I mentioned before, forward propagation is a kind of matrix calculations and activation function. But during the backward propagation, we need a lot of derivatives. Let's talk a little bit about the gradient descent. Let's assume this is a function, and gradient actually means the derivatives with respect to the whatever y or w or whatever. And we know that this is a point where g is equal to 0. I mean, I think this point could be 0 or, but this is a case where we have only one parameters, but there are many number of parameters in the backpropagation in real world. For example, let's assume this is a mountain map. This is the top of the mountain, so water will follow like that. This is water. How actually the root of this waterfall is actually the gradient of this mountain. If you are good in engineering mathematics, you can imagine that. For the simplicity of analysis, I assume that this x is the scalar, h is scalar, y is scalar, but actual case, this x is the vector, x is vector, y is vector, because there are many elements. So in n-dimensional case, gradient distance means that the vector into a direction of most steepest direction. Actually, water in the mountain flows in that direction. So this is the actually gradient in n-dimensional case. So generalization of this formalism to the n-dimensional case need a lot of vector calculations and vector matrix and vector derivatives. During your class of electromagnetics, you may be some familiar with the cross product, gradient, dot product, and cross product. We need this kind of operations. Also, sometimes, yes, sometimes derivative of vector, and there are many different operations. But the concept, even though the mathematics is a little bit complicated, but basic concept of gradient and distance are same. Now let's move on to the next case. Because in the previous lecture, I derived the equation for, update the equation for W2. W2 is here. Now I'd like to continue those mathematical derivation process for W1. In order to do that, I will do this work. Now, I derive an equation to describe the gradient of cost function with respect to W1. If we know this equation, we can update W1 using this gradient descent equation. So surprisingly, we found that this part is called delta H, and this part is delta H. So what I'm saying is, when we are updating W2, we have a ratio and delta and H. Delta H is defined by this one. And then when I am deriving this update equation with respect to W1, we have WH in the previous delta, and we have another part W2, H1 minus H, and H. H is actually hidden layer output. So now I'd like to make some summary. This is a summary of backpropagation for the case of 3-layer. We have input, hidden layer output, and Y, and target value Y dash. The connection is W1 and W2. Now, if you wanna calculate, if we have Y and Y dash and Y and Y dash, we can define delta Y, and then if we have a given delta Y, and then this, by using the previous delta and the hidden layer output and 1 minus hidden layer output and the W2, we can also calculate delta H. If we have a delta Y, we can update W2, and if we have the delta H, we can update delta W1. So I would say this is the chain rule. This is the backpropagation. So let's take a look at carefully. Let's assume that we have output and target value, and then we can define the difference of output and target value here. And y1 minus 1 is actually gradient of sigmoid function. With the given delta y, we can update W2, because with the given delta y and hidden value output and running rate alpha, we can update W2. Now, with the given, let's assume that we have delta y, already delta y, and then we can calculate the delta H multiplied by hidden layer output and 1 minus hidden layer output. You remember that because we are using the sigmoid function, output H and Y has a range of from 0 to 1. So here, and then multiply W2, we can have delta H. Then we can update W1. This is a kindly sequential. So relationship between y and delta h and this kind of connection, I call it as the chain rule. Once we build up chain rule and output of each hidden layers, we can update W at that point. This is very simple mathematical derivations, but this is applied to every type of DNN or RNN or CNN or LSTM, whatever deep neural network, the training and the optimization of weight connectivity are following exactly these procedures. I'm sure that we don't need to do these mathematical derivations. First, people who introduced CNN or RNN to deep neural network in 1990s or 2000, they did all this works. Right now, probably in the Python library, they are doing all themselves. So we don't need to worry about these mathematical calculations. But because you are engineers, if you are really good in deep neural machine learning or some applications, you should have some this kind of mathematical understanding to be more confident on your work. That is, I think, the purpose of this class in this semester. I want to give you some basic fundamental mathematical background so that when you are doing some reinforcement learning programming or RNN programming, I want to make you more confident on what you are doing. Last night, I spent some time and I did those works for the case of 5-layer case. In the previous class, right now, I show some derivation process for the backpropagation iteration equation for the case of 3-layer case. And last night at home, I spent some time to derive this backpropagation equation for the case of 1, 2, 3, 4, 5 layers case. Same, exactly same. Here also again, using the chain rule, we can define delta y, delta 3, delta 2, and delta 1. And very similar equations, update equation, we can do up to 1000. As soon as we build up chain rule, the calculation of this more deeper layer case are very straightforward. Once we define delta y for more than 100 case, the iteration of this W4, W2, W1 is very straightforward. Once again, I would like to emphasize that in this case, for the simplicity of mathematics, I show you the derivation process for the backpropagation for the case of single node numbers. That means the scalar case. But as I show you in here, this is the case of scalar, but n-dimensional case is more like a vector calculus. And it will need more space concepts and we need more index and tensor operations, but basic concepts are same. Those are the summary of class right now. So I would like to complete this backpropagation class right now. So, in order to generalize this backpropagation, it's really depending on cost function and In order to, let's assume that you initially design a deep neural network model, you have to uh, generalize this backpropagation process of this update equation. In order to that, it is depending on cost function. So you gotta be carefully decide your cost function. There are many different types of cost functions, so you have to select them. Sometimes you have to learn from your previous students, or you can build up your own experience, or sometimes you can read textbook or some recent papers. Then you can learn from that. Sometimes you can buy some libraries and you can apply for that. And also, you can choose your own activation function. In this case, for the simplicity of analysis, I used mean square error and the sigmoid function, but that is on case. There might be hundreds or thousands of different cases. And if we have really super computer power, we can, this cost function, choice of this cost function and activation function could be also, computer can do that. As I mentioned before, time machine in our digital world is computer. If we have more computers, more strong computer, we don't need to worry about cost functions, activation function. Computer itself can find it. So that's why Google and IBM is trying to find a new computer machines called quantum computing. They are not using the GPU and DRAM at some point, but I'm not sure how much quantum computing can replace our own digital computing. And it may take more time for quantum computing to replace our digital computing, because in order to use the quantum computing, we have to cool down the computer near the absolute 0 Kelvin temperature. It takes huge cooling system, air conditioner, liquid heliums, and in our daily case, we can this is a kind of computer, and we can bring it to everywhere. But quantum computing, we cannot do that. But anyway, during the development process of deep neural network, I think we initially model developers should spend some good amount of time to find what is the best cost function and what is the best activation function. Depending on the cost function selection and activation function selection, it will be we will have different formulation than this. Also, in this derivation process today, I used just scalar case, just number, not vector x and h and y was not vector. It is a kind of just scalar number. That's why our derivation process is very easy. But in order to generalize this backpropagation equation, which I was shown up here today, is that we should be able to manipulate vector and matrix operation. For example, here, we use the scalar derivative for update equation, but generally W vector and W matrix can be updated using gradient. See, the formalism and the description will be a little bit complicated. But if you are good in electromagnetic class, then you may be much easier. So, also for the general case, number of nodes and number of layers could be many different numbers. So we should be able to generalize that. Now, because of this fact, I would like to spend some time for the talk about cost function and activation function. That is the remaining part of the class today. Last night, I wrote it down already. There might be many different type of activation function. One of that we used today is the logistic, in other words, sigmoid function. This is good for classification because its output is between 0 to 1. 1 means the output is the tiger, 0 means output is the cat. So it is more useful for classification. Another important feature of this sigmoid function is that derivative is represented by itself and 1 minus itself. So mathematical calculation of derivative is very easy. That's why probably is initially many people and many machine learning scientists use the sigmoid function because it is good for classification. Actually, many purpose of this deep neural network is the classification, whether it is a tiger or cat or something. So we can use this logistic sigmoid function, and then also derivative is very easy. And in the previous derivation, there were always a term called y1 minus y or h1 minus h. Actually, it is coming from derivative of sigmoid function. Chain rule is very simple and easy. So even though computer has a superpower, sometimes to make a much faster determination of output of deep neural network machine learning, we sometimes need to have some simplified chain rule backpropagation. Simplified the derivative means the simplified chain rule, and it will result in this fast backpropagation. Another type of activation function is tangent hyperbolic. As I remember, that is usually used the recurrent neural network. Recurrent neural network is the very starting point of interpretation of our language. Now, transformer learning and more advanced learning is replacing this RNN to make an interpretation of language using machine learning. But transformer learning, which is very recent, powerful natural language processor of machine learning, it transformer learning need more and more computing power. And that's why I told you that computing power is really time machine. And in this case, it has the range -1 to 1. So it is also good for classification. Somehow, sometimes we cannot easily explain why tangent hyperbolic function is good for RNN and other deep neural network need the sigmoid function. I think it is quite heuristic. Somebody did that and it works good, and then they follow it. There are not concrete theories yet. And in the tangent hyperbolic function, definition is like that. The lower part is cosine hyperbolic x, probably upper part is sine hyperbolic x. That is the kind of definition. If x is becoming complex number, it's actually become cosine function, sine function, something like that. Also, good thing about this tangent hyperbolic function is that derivative of this function is 1 minus self square. So probably next week, I'm gonna work on the backpropagation of RNN. Also, I'm going to spend some time on backpropagation of RNN. At the time, I'm gonna use this equation. Today, during the derivation of backpropagation, I used this equation. But next week, when I'm gonna spend on the lecture on RNN, I'm gonna spend this equation. So my point is that depending on model, deep neural network model, activation function will be different, then chain rule will be different. Sometimes, but there are some disadvantages of this activation function. What is that? Because when x is large, near 1, almost the derivative of this one becomes 0. You see that if this is saturated, if x is large, derivative of this function is really small. And also here you see that if x is fx, this is really near the 1, this becomes 0. If x is minus infinite, also this is becoming to 0 because slope, this is actually slope of this activation function. So let's assume that this is the optimal point after the backpropagation or training. Initially, this gradient is really small, that means it takes longer and longer time to make a backpropagation, and eventually it has to go back to this optimal point, but somehow derivative is too small. Even though we use this, if this derivative is very small, it takes much longer time to reach to optimal point. That is a little bit, sometimes there are other techniques to compensate this method, but those are some disadvantages of differentiation. Is beautiful. Exponential function has a beautiful feature because exponential function derivative becomes itself. That is the beauty of sine function, sine x derivative of sine x become cosine x derivative becomes sine x. So derivative of triangular function becomes triangular function. Actually, triangular function is the exponential function with a complex number. You see that derivative x is becoming ex. This kind of beautiful feature. And because of that feature, we have some this kind of beautiful functions. So derivative is easy, but sometimes at the extreme case, when fx is near 1 or fx is near 0, it's becoming very slow. So iteration will be very slow. So in some cases, linear function is much better. Linear function is much better because derivative is only 1. This derivative is really near 0, that means the gradient is vanishing. We call it vanishing problem. Vanishing. We call it vanishing problem. Derivative is almost 0, but linearity case is always just linear. So it is good sometimes. So sometimes we can use identity. Then in the case, derivative is just simply a constant. Another activation function is called ReLU function. It is used CNN. There is some clipping feature because this property is actually coming from synapse. Let's assume I have a finger. If I press this, at certain point, I don't feel any anything, any pain. But if I put at over a threshold, oh, I feel pain. Like that. That is, I think that is the operation principle of synapse in our brain. So up to a point, it doesn't propagate. Up to a certain threshold, it propagates. Here is the propagation. Here is the non-propagation. So up to a certain threshold, it is not propagated. Up to a threshold, it propagates. That is the kind of property of this function that is called rectified linear unit, and that is called ReLU function. That is being used in CNN. Probably at the first week of April, I'm gonna spend some time on next 2 weeks. I'm gonna spend time on RNN, and then I'm gonna spend a couple of weeks for CNN. Even though RNN and CNN is a little bit simple and we can easily understand that operation, but those are basic building blocks of AlphaGo or very advanced deep neural network algorithm. Most important building block of deep neural network training is backpropagation. And in order to be able to understand backpropagation, we have to understand the derivative of the activation function and cost function. Today, to finish my class, I was talking about activation function, and on Wednesday, I'm gonna spend more time on cost function. There are, in the simplicity of analysis, I used the mean square error function. In this case, we use the mean square error function. Because of that, initially this term came from the mean square error. y minus y dash. You remember that this is the definition of cost function. Derivative of this actually came to y minus y dash. That's why we have this term here. And also in the in this chain rule, always we have this one because of the choice of our cost function. But in actual world, there are cross entropy, entropic activation function, and log likelihood function, and softmax function. Depending on whether you are developing CNN or other deep neural network or RNN, you have to use different type of cost function. And once again, CNN, RNN are very simple compared to advanced deep neural network, but by understanding this, we can build up them. This is really good building block of deep neural network. And on Wednesday, I'm going to spend some time to compare mean square cross entropy, logically likely, and soft max function. This is the end of my class today. Thank you for your attention. Also, I'm going to announce some, there will be some announcement, and TA will help you. I think I will ask you to form a group to conduct a term project in this semester. See you on Wednesday. Thank you for your kind attention.